In section 1.2, we look at the common phases of matter and what make those phases different from one another, and also different ways in which matter is classified. So earlier we said that chemistry is the scientific study of matter, its properties, and its transformation. So an important question to ask is, what is matter? And perhaps the most well-known definition of matter is that matter is anything that occupies space and also has mass. Sometimes people, instead of saying occupies space, they will say has volume, because volume is just a measure of the amount of space that an object takes up. So mass is the quantity that describes the amount of matter in an object, that is the number of atoms, the number of molecules that make up that object. It's useful to chemists because the mass of an object will be constant at every place in the universe, because it's just the number of particles that make up that object. In the lab, how we measure mass is using a device called a balance. At home, we tend to call this a scale. It's called a balance because back in the day, people would use things called beam balances. When the masses on either side of a beam are equal, the beam will stay perfectly horizontal. In the lab, we use digital balances, and the digital balances that we use are good to 3 decimal places. This means that they're pretty sensitive, so if you do lean on the table while you're making measurements with these guys, you'll find that they'll flicker around a bit. So when you're using the balance in the lab, try not to lean against the table as you're trying to record the mass. You'll also see that our balances have a little wind guard, because air currents will actually cause the mass to flicker around when you're measuring to 1/1000th of a gram. And you can see this if you wave your hand over the top of the balance, it'll flicker a little bit as you move the air around on top of the balance. So again, if your mass measurement is flickering around a little bit, consider using the little guard that stops the wind from blowing across the balance, and it will help stabilize your measurement. The weight of an object describes the force of gravity acting on it. And because gravity varies with location, it's not so useful to chemists because, we want a constant quantity. So a good example of weight varying with location is if we consider the weight of a person when they're on the Earth versus when they're on the Moon. And there's a difference of about 1/6. Obviously, the person has the same mass in both locations, but the gravity acting upon them is different. If we take a person and put them in outer space, where there's no gravity acting on them, they'll actually be weightless. It's even worse than this. Your weight also varies with the forces acting on you due to the way that you're moving. So you've probably felt yourself become heavier when you are decelerating hard. When you hop in that elevator and it stops moving downwards, you can go, whoa, you get that heavy feeling in the pit of your stomach. And you might have felt that weightlessness when you're free falling like on a roller coaster. So weight, not so helpful for chemists because it's kind of all over the place depending on where the object is located and depending on how the object is moving. But an important scientific law for chemists that's related to mass is what we call the law of conservation of matter. The law of conservation of matter states there is no change in the quantity of matter, that is the mass of an object, present when matter converts from one type to another, that is during a chemical change, or when matter undergoes a phase or any other kind of physical change. So a good example of this was an experiment that was originally done by a guy called Antoine Lavoisier way back in the day. He was a Frenchman. And if you take some mercury oxide and you put it in a sealed tube, it's just kind of a yellow solid. It's highly toxic, so you probably wouldn't do this nowadays. Put that in a sealed tube, and then we heat it up with something like a Bunsen burner. What you'll see is that the mercury oxide will decompose to form liquid mercury. It's just there in the bottom. and oxygen gas. However, the total mass of the whole system doesn't change. So if you weigh this before you heat it and then weigh it after you heat it, you have the same amount of stuff there, even though a chemical change has occurred. So this is a great example of the law of conservation of matter. So matter commonly exists in one of three states: solid, liquid, and gas. And you could probably recognize these things if you saw them, right? We know what solids look like. They're kind of rigid. You can poke it and it's not squishy most of the time. We know what liquids are like. Liquids you can pour from one container to another and they flow. And we know what gases are like. They're these kind of nebulous things. They kind of spread out. If you poke it, your finger just goes straight through. We know how to distinguish using our senses a solid from a liquid from a gas. An interesting question to ask is, how is temperature related to the state of a substance? Now, you probably recognize that when we heat an object up, we increase the extent to which the particles making up that object are moving. So you probably recognize that solids form at low temperatures, which is interesting, which means it tells us that the particles that make up solids are not moving around a lot, right? Because low temperature means low movement. You probably know that if you want to make steam, then you can take some water and you're going to heat it up. So gases form at high temperature, which is telling us that the particles that make up gases are moving around a lot. Right? The particles that make up gases are moving around a lot because gases exist at high temperature. Now, what about liquids? Well, let's just think about water. Steam exists at really high temperatures, above 100 degrees Celsius. Ice exists at temperatures below 0 degrees Celsius at really low temperatures. Liquid water exists in between those two temperatures. So intermediate temperatures are where we see liquids. So what we would expect is that the particles that make up liquids are moving around more than those that make up solids, but less than those that make up gases. So that's a cool little bit of scientific reasoning, because by thinking about how temperature affects the extent to which the particles are moving within an object. Another interesting thing to consider is, how is pressure related to the state of a substance? So if I took a gas and I applied a pressure to it and pushed all the particles closer together, what we find happens is that my gas will get transformed into a liquid. So that's telling me that the particles that make up a liquid are closer together than the particles that make up a gas. If I continue to apply a pressure to a liquid, eventually it will become a solid. So again, what that's telling me is that as I push the particles closer together by applying a pressure, we'll move from liquid to solid. So therefore, the particles that make up solids have less space between the particles than the particles that make up a liquid. So that's kind of cool. Okay, so let's do a deep dive and look at some of the specific properties of gases, liquids, and solids. So gases are interesting. Gases have a variable shape. The shape of a gas is just the shape of its container. But what makes gases unique amongst the three common phases of matter is that a gas will fill whatever container it's placed in. That is, gases have what we call variable volume. If you put your sample of gas into a bigger container, it will spread out to fill that container. And gases are the only state of matter that has a variable volume, which is why we do a whole chapter on gases in chapter 9, right at the end of the quarter. So an interesting question to consider is the density of a gas fixed? Can we change the density of a gas? And I hope what you can see is that because there's a lot of space between the particles that make up a gas, if we were to push on our sample of gas, we could push these particles closer together. That is, we could compress our gas. So the density of a gas is not fixed. We can compress gases. Now, in liquids, the particles are a lot closer to one another than they are in gases. So what we'll observe is that the density of liquids is greater than that of gases. And that's not that surprising. We know that if we have a balloon that's full of air, it doesn't weigh as much as a balloon that's full of water. You've probably observed that, right? Liquids are kind of cool because they do adapt to the shape of their container. You pour a liquid from one container to another, it'll change shape. That's kind of cool. However, unlike gases, liquids have a fixed volume. And that's actually really helpful for us in the chemistry lab because we can use devices like graduated cylinders to measure the volume of a liquid, and then we pour that liquid into another container, and we know that the volume will not change. So whatever we have in our original container is what we're going to get in our second container. So gases have variable shape, but fixed volume. So is the density of a liquid fixed? Well, if we were to apply a pressure to a liquid, you can see there's really not much space between the particles. So it's very hard to compress a liquid. So for that reason, at a given temperature, we find that the density of a liquid is fixed. And you can test this yourself. If you grab a water bottle that's full of water and try and compress it, you really can't compress it. There's just not a lot of space between those water molecules. So gases are the only state of matter that has a variable volume and a variable shape. Solids are unique in that they have a fixed shape and a fixed volume. In solids, particles are very, very close to one another. There's really no space between the particles. So for this reason, solids have high density in general compared to liquids and gases. There's just not a lot of empty space between them. You can see this cartoon is attempting to show that solids have their own shape. It doesn't matter the shape of the container, the solid has a fixed shape. So when we think about this question here of can solids be readily compressed, well, if we apply a pressure to a solid, we really can't push the particles any closer together. So for that reason, we say that solids cannot be compressed. Okay, so to understand the different classifications of matter, we need to review what is called the atomic theory of matter. So in modern chemistry, we take an atomistic view of matter. And the first written record of this idea was written down by a guy called, or the one that we kind of know of, there probably was earlier ones that have been lost. The first time that this, as far as we know, was written down by a guy called Democritus, sort of 3,000-ish years ago. And basically what we're doing in an atomistic view of matter is we're describing matter as being composed of particles. We call them atoms. They're little tiny building blocks that can't be divided by either physical or chemical methods. So basically what we're going to say is we've got a bunch of different shaped building blocks, and we can put those building blocks together in different ways to build up all of the objects that we see around us. So we might build something like that, or we might build something more like that. Okay, but we're just going to use our little set of building blocks to build up all of the things that are around us. Now, the little building blocks themselves can't be divided by any physical or chemical method. So we probably need to define what we mean by physical methods and chemical methods. So physical methods of division are methods of division that don't involve breaking connections between atoms. So when I slice a piece of cheese off, I'm not breaking connections between atoms. So therefore, slicing or cutting an object would be described as a physical method. A chemical method is one where we break connections between atoms. So for example, if I took this object here and broke it apart into its component atoms, then I would be dividing this using a chemical method. So once we have this idea of atoms in place, we can start defining different categories of matter. A sample of matter can be characterized as being either a pure substance, sometimes we will just say a substance, or a mixture. And what a mixture is a physical combination of more than one pure substance. And you can tell you've got a mixture because the different components can be separated by physical means. Okay, they can be separated by physical means. That is, the different components can be separated without the need to break connections between atoms. So just summarizing these ideas, if we have a sample of matter and it can be physically separated into different things, then we have what we call a mixture. If we have a sample of matter and it cannot be separated into two or more different things, then we have what we call a pure substance, or sometimes people just call that a substance. Now, a mixture is different from a pure substance because mixtures can have a variable composition. For example, you might make a cup of coffee really strong if you're feeling quite sleepy, or you might make a cup of coffee quite weak if you're worried about being kept awake at night. It's still a cup of coffee whether it's weak or strong. If you like to have a mixed beverage every now and then, you probably know that you can make it with a lot of booze in it or just a little bit, depending on what your mood is and what's been going on in your life. If you're a painter, you might have mixed different colors of paint together to get new shades. And the color that you get depends upon how much of each pigment that you combine. It's still paint though, right? Because paint is a mixture, so we can have a variable composition. Mixtures are often categorized as being homogeneous or alternatively as being heterogeneous. In a homogeneous mixture, a sample of any part of the mixture appears exactly the same as any other sample. A good example of this is if I dissolve sugar in water. If I put a spoonful of sugar in water and I give it a good stir, it looks the same from top to bottom. It's going to be just as sweet at the top as it is in the middle, as it is in the bottom. Another example of a homogeneous mixture is an alloy. In an alloy, what they do is they take a couple of different metals, heat them up until they all melt, give it a good stir, and let it solidify. And if it's done correctly, you'll see that there's an even composition throughout the alloy. One part of the alloy appears exactly the same as any other part of the alloy. Homogeneous mixtures are sometimes referred to as solutions. So you'll see people using those terms interchangeably. Heterogeneous mixtures have visibly different parts. A good example of this would be oil and water. And you can kind of tell you got a heterogeneous mixture because a sample of one region might have has an obviously different composition from a sample of a different region. So if you have that sample of oil and water, you probably know that oil floats on water, and you can see that there are very different regions within our mixture. So the components that make up a mixture can be separated using physical methods because the different components are not chemically bound to one another. Three common methods for separating the components of a mixture are distillation, filtration, and crystallization. So typically in distillation, what we'll do is we'll apply some heat in order to evaporate one of the volatile components. So we do this most commonly in the lab to distill water. We produce large volumes of distilled water by taking tap water, heating it up, the water evaporates, we condense the water, and then we put it in big containers and leave it in the chemistry lab for you. We can make about 11 gallons of this every hour. Another common method for separating the components of a mixture is to use filtration. In filtration, we're normally trying to separate a solid from a liquid. So we'll just pass our mixture through a filter. Often it's what we call a filter paper, and the liquid will run through and the solid will get caught on the filter. You're doing the same thing at home when you use a colander to separate pasta from water. Towards the end of General Chemistry 1, we're going to be taking advantage of what we call crystallization to separate a solid from a liquid. So some solids are soluble at high temperature, and insoluble at low temperature. So what we can do if this is the case is we can take a solution of our solid at high temperature, put it in some ice, cool it down, and our solid will crystallize out, and then we can take that mixture, pass it through a filter, and collect our solid. So you'll have the opportunity to use all of these techniques this quarter. Pure substances, or sometimes just referred to as substances, can be classified as being either elements or compounds. Elements cannot be broken down into simpler components by either physical methods or chemical methods. And this is because they are pure substances composed of only one type of atom. Compounds, however, can be chemically broken down into multiple components. And that's because they're pure substances composed of more than one type of atom. So that's the distinction between these two types of pure substances. So putting everything together into the one diagram, if we have a sample of matter and it can be physically separated into multiple different things, then we have a mixture. If we have a sample of matter and it can't be physically separated into multiple different things, then we have a pure substance. If our mixture has a uniform composition, then we're going to describe it as a homogeneous mixture, sometimes referred to as a solution. But if our mixture has visibly distinct parts to it, we're going to describe it as a heterogeneous mixture. If we have a pure substance and we find that it can be chemically broken down into multiple different types of atoms, then we have a compound. But if our pure substance cannot be broken down chemically into multiple different types of atoms, then we have an element. Now, you're going to see that we're going to continue to divide elements and compounds into different categories, but we're pretty much done with our mixtures. We're not going to divide those into any further categories. So returning back to our atomic theory, we now know that there are 118 different kinds of atoms that make up all of the elements and compounds in our universe. Every type of atom has its own symbol. The first character in an atom symbol is always an uppercase letter. Most of the atoms have a second character, and if they do, that second character is always a lowercase letter. So, these are some typical examples. Uppercase followed by lowercase. Uppercase, just because it's a one character symbol. Uppercase followed by lowercase because we've got two characters. So every time I see an uppercase, I know that I'm beginning a new atom type. So if I saw K, S, R, N written like that, I would know that that was the division between the types of atoms. Most elements are found in nature as individual atoms. However, there are 7 elements that are always found in nature as diatomic molecules. These are often referred to as the diatomic 7. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. One way of remembering them is to remember that there are 7 of them, to go over to element 7 and draw a 7, and that gives you 6 of them. It only gives you 6 of them. You have to remember the hydrogen is also a diatomic. The other way is the little phrase, have no fear of ice cold beer, and that corresponds to hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. So hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine, have no fear of ice cold beer, gives you the diatomic 7. We also need to remember that phosphorus is always found in nature as groups of 4 atoms, kind of forms a triangular based pyramid with phosphorus atoms at the corners. And then sulfur is always found in nature in groups of 8 atoms bound together, and it forms little rings of 8 atoms, which is kind of interesting, isn't it? So it looks like that. Kind of tricky to draw, actually. 1, 2, 3, 4, 5. Something along those lines. I think we got close to our 8 in there. Maybe we're missing one. We need an extra one there. There we go. Now we've got our 8. All right, but sulfur is found as rings of 8 atoms. A compound is 2 or more different atoms chemically bound together. The important thing to recognize is that the elements present in a compound are always in a characteristic ratio for that particular compound. For example, ammonia will always have 3 hydrogen atoms for every nitrogen atom. And we indicate that when we write the formula. Anytime there is more than one of an atom present, we use a subscript number to indicate the type of that atom or the number of that atom that is present in that particular compound. It's important to recognize that the elements that are present in a compound can only be separated from one another by chemical methods. That is, we have to break connections between the atoms in order to separate out those different types of atoms. So let's have a look at an exercise from the OpenStax book. It says, what properties distinguish solids from liquids, liquids from gases, and solids from gases? So whenever you have a question and it's got multiple question marks in it, always make sure you answer all of the bits. So what distinguishes solids from liquids? Well, liquids have a variable shape. Solids don't. Now you could also have mentioned something about density if you wanted to, but I think that that's probably the obvious one. I've labeled it as A. It's not really A, is it? But I guess we can kind of think of it as being A, B, and C here. Liquids from gases. Well, gases have a variable volume. Liquids don't. We could also mention something about compressibility. Gases are highly compressible, liquids are not. And finally, solids from gases. Well, I think the obvious one is solids have a fixed shape. Gases don't. But there are other things. We could talk about volume, we could talk about variable density. You know, there are other things other than shape that we could have mentioned there. So here's the answer that OpenStax give. It says liquids can change their shape or they can flow, solids can't. And that's exactly what I wrote. Gases can undergo large volume changes as pressures change. Liquids do not. And I said something similar. I said gases have a variable volume. Liquids don't. So that looks like it's correct. And then finally, they said gases flow and change volume. Solids do not. And I picked a different way of tackling this problem. I said solids have a fixed shape, which I guess relates to flowing. Gases don't. So close to the same, but not quite. Anyway, I feel confident in those answers. It's an interesting problem from OpenStax and a really common problem on quizzes and tests. It says classify each of the following as an element, a compound, or a mixture. Now, you do need to use a little bit of sort of general chemistry knowledge here. Iron is an element. Fe is the symbol for iron. Oxygen is also an element. It's one of our diatomic elements. It's made up of a single type of atom. Mercury oxide, we mentioned this earlier when we were talking about the law of conservation of matter. It's made of mercury atoms and oxygen atoms. It is a compound. Pancake syrup, which is kind of the fake maple syrup stuff, made up of a whole bunch of different compounds. It's got some water in there, probably got some fructose in there, it's got some colouring in it to give it that nice brown colour. Clearly made up of many different things. So we're going to classify that as a mixture. So it looks like they agree with me. I got each of these guys correct. This is another question from OpenStax, and they're asking about the distinction here between what we mean by the term weightless versus massless. So it reads, why are astronauts in space said to be weightless but not massless? So we're going to answer two things here. They are said to be weightless as they are not acted upon by gravity. So they are not massless as they have, or let's put it this way, are made of matter. And matter always has mass. There we go. Okay, so that concludes the video for section 1.2. I hope you found it helpful.